Welcome everyone. I'm excited to kick off today's presentation on real-time credit card fraud detection. This is the first slide, the cover slide, where we set the stage for what's to come. We'll be exploring how cutting-edge technology helps identify and prevent fraud as it happens. Over the next few minutes, I'll walk you through the main concepts, the challenges, and the innovative solutions that are shaping the future of secure transactions. Let's get started. Let's start by looking at the problem statement. As digital payments continue to grow globally, credit card fraud is on the rise. This increase creates direct monetary losses for both card issuers and merchants, and it also damages customer trust, which is crucial for the success of any financial institution. Many smaller issuers still depend heavily on static, rule-based systems. These systems typically flag transactions based on hard thresholds, like an amount exceeding a certain limit or transactions happening overseas. While these rules can catch some known fraud patterns, they struggle with more subtle, evolving, or adaptive fraud tactics that change over time. Fraud itself is constantly evolving at a rapid pace. This means we need systems that can learn and adapt dynamically as new fraud patterns emerge. Our goal is to build a machine learning model capable of detecting fraudulent transactions in real time. This model should identify unusual, anomalous patterns and adapt to new tactics more effectively, ultimately reducing fraud losses and decreasing false declines for legitimate transactions. This presents a significant opportunity to improve how we combat fraud. By moving beyond static rules to intelligent, adaptive systems that can keep pace with the evolving threat landscape. Let's start by looking at the data availability and the signals we can leverage for fraud detection. Financial institutions generate a huge amount of structured transaction data, including details like the amount, merchant, time, location, device used, and the customer's prior transaction history. This rich data provides a strong foundation for machine learning models to learn from. We also have access to historical labeled fraud examples, such as chargebacks and confirmed fraud cases. These examples serve as valuable signals, helping the model distinguish between legitimate and fraudulent behavior by recognizing patterns. Now, why does this matter from a business perspective? Even small improvements in reducing fraud rates can lead to significant cost savings. Plus, improving the accuracy of fraud detection means fewer false positives, which translates into a better experience for customers and higher retention rates. So, the overall business impact of deploying ML here is quite substantial. Moving on to feasibility and operational fit, it's very much within reach. Modern streaming and cloud systems allow us to score transactions in real time, which is crucial for timely fraud prevention. Many banks already have existing points of integration for making fraud decisions, like blocking, challenging, or allowing transactions. Of course, there are technical and regulatory considerations, but they are manageable. With proper system design, focusing on explainability, logging, and respecting latency limits, we can implement these solutions effectively and compliantly. All of these factors combined make ML a very compelling fit for fraud detection in financial services. On this slide, we're focusing on the expected business impact, which we can think of in a few key areas. First, we aim to reduce monthly fraud losses, which directly improves our bottom line. We also want to cut down on chargeback processing costs, making our operations more efficient. Additionally, by reducing false declines, we can enhance the user experience, preventing legitimate customers from feeling frustrated or turned away. Moving to the outcome metrics, we're looking at the percentage reduction in monthly fraud losses, so how much we're actually saving in monetary terms. We also want to see a decrease in our chargeback rate and the associated operational remediation costs. And of course, we monitor customer complaint rates and false decline rates to ensure we're not harming our users. On the model side, we measure recall, which is the true positive rate, basically how well our model detects actual fraud. Prioritizing high recall is crucial because catching fraud is our top goal. But we also need to focus on precision, which helps us limit false positives and avoid declining legitimate transactions. Additional metrics like the F1 score, AUC ROC, and the false positive rate give us a balanced view of the model's performance. Latency is another critical factor. Our system needs to process transactions quickly, ideally under 200 milliseconds, to meet operational service level agreements. We also face constraints such as class imbalance, since fraud cases are rare, and regulatory considerations around data privacy and explainability. Plus, we need to ensure our system integrates smoothly, works within our compute budget, and maintains high availability. Finally, defining success involves setting clear outcome and output metrics, along with these constraints, so we know whether our fraud detection system is truly making a positive impact. This comprehensive approach helps us balance business goals with technical and regulatory requirements. Let's dive into the engineered features that power our fraud detection model. First, we look at the ratio of the current transaction amount to the customer's average, which helps us identify unusual spending behavior. Then, there's the time since the last transaction. Long gaps or rapid successive transactions can be red flags. We also analyze the rate of amount change, or delta, to spot sudden spikes in spending. Another important feature is the distance between the billing address and the transaction's geographical location. Large distances in a short time frame might indicate suspicious activity. We also track aggregated velocity counts, such as the number of transactions in the last hour or 24 hours, to catch rapid bursts of activity. We incorporate composite risk indices derived from various rule-based heuristics, giving us an overall risk score. Moving beyond transaction-specific data, we consider external or contextual features like real-time blacklists, whether the merchant or IP address is flagged, and recent global or regional fraud outbreaks. Whether conditions or holiday signals, if relevant, can also influence transaction patterns. Customer behavior is another critical aspect. We analyze their typical spending patterns, preferred card usage times, past fraud history, and the distance between their transactions. These insights help us understand what's normal for each customer. When it comes to transaction data itself, we look at the amount, timestamp, merchant category, device used, location, and frequency patterns. All these features collectively help us build a comprehensive picture. Finally, among all these features, some stand out as most important for our fraud model. They include the ratio of current to average spending, transaction velocity, and external risk indicators. By focusing on these key points, we can more effectively identify potential fraud while minimizing false positives. So, moving on to our solution concept, the core idea is to develop a supervised classifier that assigns a fraud risk score to each transaction as it comes in. Based on this score and predefined policy thresholds, the system can take different actions. It can allow the transaction to proceed, require an additional step-up authentication like an OTP, or block the transaction altogether, or send it for manual review. Next, let's talk about how we validate this solution through an iterative experiment plan. First, we start with a data feasibility check. This involves exploring historical labeled transactions to test basic models and confirm that there's a predictive signal we can leverage. Then, we move into prototype and offline testing. Here, we train different models like logistic regression, random forest, and gradient boosting machines, comparing their performance against rule-based systems using metrics like precision, recall, and false positive rate. After that, we perform shadow deployment, where we score live traffic without actually taking action. This helps us monitor key metrics such as the fraud catch rate, false positives, and latency, ensuring the system's performance in real-time conditions. Following that, we can conduct A/B testing or a canary trial by routing a small percentage of transactions through the machine learning system. This allows us to measure the actual reduction in fraud loss and observe any impacts on the customer experience. We also include a threshold and human-in-the-loop phase, where we fine-tune decision thresholds and use manual review feedback to improve our labels and model accuracy. Finally, once we're confident, we scale the rollout gradually while continuously monitoring for data drift. evaluating performance, and periodically retraining the models to keep them effective. This validation plan ensures we iteratively refine our approach, balancing security and customer experience, and ultimately deploying a robust, adaptive fraud detection system. Let's talk about the differences between cloud and edge systems, starting with the cloud system. In a cloud setup, we benefit from centralized data access, which makes training scalable and allows us to maintain a feature store efficiently. This setup supports real-time scoring and enables us to gather global threat intelligence, giving us a comprehensive view across all transactions. On the other hand, edge devices are less suitable for complex models or frequent updates because of their limited processing power and storage. Looking at the architecture at a high level, data flows through a streaming ingest process into the feature store. From there, the real-time scoring API kicks in to provide instant predictions, which then feed into the decision engine and logs for monitoring and further analysis. Moving on to training methods, we typically rely on offline or periodic retraining, which gives us a robust foundation for model tuning and validation using historical labeled data. Since fraud labels often arrive with some delay, offline training naturally fits this scenario. That said, we also have the option for incremental updates, which help us quickly adapt to new fraud trends without waiting for full retraining cycles. Finally, in prediction mode, we focus on online, real-time scoring. Each transaction needs to be scored instantly, often within just milliseconds, to ensure a seamless user experience and timely fraud detection. We reserve batch processing for analytics and monitoring, not for making primary decisions. This setup ensures our ML system is optimized for speed and accuracy, supporting the overall goal of proactive fraud prevention. Now let's look at some of the potential risks in production and how we can mitigate them. First, there's class imbalance and label quality. Since fraud is quite rare, our models can become biased, and delayed or noisy labels can further impact performance. To address this, we use techniques like class weighting, upsampling, stratified sampling, and review-validated labels to improve accuracy. Next, concept or data drift is a common challenge. Fraud tactics evolve over time, which can reduce our model's effectiveness. To combat this, we monitor key metrics and feature drift, and we perform scheduled or trigger-based retraining. Shadow testing also helps us validate updates without risking production. Adversarial behavior is another critical issue. Fraudsters are constantly trying to evade detection, so we adopt multi-layered defenses like device fingerprinting, multi-signal features, combining machine learning with rule-based systems, and incorporating human review for tricky cases. This layered approach makes it harder for fraudsters to succeed. Then we have training-serving skew, which occurs when there's a mismatch between the data used during training and what the model sees in production. To mitigate this, we maintain a unified feature store, implement schema checks, and use versioning to ensure consistency. Latency and availability are vital, especially for real-time scoring. We need our models to be both fast and reliable. We achieve this through redundant endpoints, caching strategies, and model optimization or distillation techniques to speed up inference. False positives and negatives can impact user experience or cause financial losses. To minimize these, we perform threshold tuning, implement step-up authentication when necessary, and conduct manual reviews for edge cases to strike the right balance. Finally, privacy and compliance are paramount when handling sensitive data. We ensure PII is securely masked, maintain audit logs, and adhere strictly to policies and regulations, safeguarding user data throughout the process. By understanding and addressing these risks proactively, we can build robust fraud detection systems that are both effective and trustworthy. Thank you for joining me today. I really appreciate your time and attention throughout this presentation. I hope you found the information valuable and thought-provoking. Remember, the key points we've discussed highlight the importance of understanding the core concepts and how they connect to the bigger picture. If there's one thing to take away, it's that applying these insights can make a meaningful difference in your work. So again, Thank you very much for being here. I look forward to any questions or discussions you might have.